Good day. Thank you for joining us. And today I would like to give a presentation on various OPC UA security concepts. And I want to dig down at a deeper level than you might have seen in other presentations. And the audience that I'm primarily focused on are system integrators, basically people putting together UA systems and debugging problems with it, as well as developers or people developing applications that would need to integrate with other off-the-shelf applications, where you're trying to figure out how to take advantage of OPC UA, as well as people who have to configure and manage their systems and all the UA applications that are running on their network. So I'll start with sort of a general discussion of the key security concepts which have gone into the development of the OPC UA security model. The first tier of this has to do with trusted information. This is communication security, ensuring that the information that gets put on the wire is kept confidential, it can't be changed, and there's reasonable protections against denial of service attacks, either inadvertent due to misconfiguration or deliberate because of a malicious actor or actors. The next tier has to do with access control. It's great that you can communicate and your communication is protected, but how do you know who you're talking to and what they're allowed to do? That's the authentication and authorization duality. And then, even though you've figured out who somebody's talking to and you figured out they're authorized, if something goes wrong, you need to go back later and do some sort of forensic analysis to figure out where this intrusion came, what happened, and what they're able to do while that intrusion happened. You needed to have some sort of audit trail. And this is all part of the OPC UA specification. How do you collect this information? Where do you record it? And the last tier is perhaps the most important aspect of every security solution. You can have all of these building blocks, which are absolutely essential in terms of ensuring integrity of communication, authenticating users. But if you don't have a sensible way to configure everything, then you just have this nightmare, administrative nightmare, that you can't deal with, and you end up being forced to turn security off. And so I'm going to be talking quite a bit how OPC UA makes life easier in terms of managing the configuration problem. Now, it's worth discussing the security environment that we're dealing with, sort of the typical network infrastructure, which is not typical of IT networks. It's not typical of IoT applications. It's a hybrid that has its own unique characteristics. And these are important to keep in mind when we're talking about security in an industrial automation setting. Specifically, you'll have these tiers of networks, where at the lowest level, you'll have this control network, where you'll have that will be a bunch of devices that are responsible for doing some specific operations, such as a specific process line or specific assembly line. And there'll be an isolated network to make sure that there's no minimize the risk of accidental traffic interfering with the operation of these devices. Multiple versions of these control networks may be in a factory, and then it will be all linked together to an operations network, where you'll have your more supervisory applications in place. So your MES, your SCADA systems. More and more what we'll see is these edge servers. And these edge servers are basically these gateways that handle the interactions with the internet. What you'll never see is factory devices being put directly on the internet in sort of the traditional IoT situation. That just doesn't make sense from a security perspective. It doesn't make sense from an operational perspective in terms of how you manage the devices. And so there's almost always going to be these gateways that are going to be deployed and end up being part of the operations network. The corporate network, where you have your connection back to your purchasing department and your a sales department and other sort of corporate level tasks. This is treated as kind of an external untrusted network as far as the as far as the factory is concerned, because there's too little restrictions on what traffic could be going across those corporate networks. And so the firewalls that I put in here, they will show up in some systems, they won't show up in others, they'll just be simple routers. It really depends on the security requirements, but conceptually you do have these tiers, and then separate from these tiers, you'll have these very isolated connections to the cloud to accomplish a certain task. So you'll have the edge gateway in place that will be pushing data up to an analytics application that is a combination historian and does performance analysis, QA analysis, and various other useful tasks that can be done when you're given tons of data to analyze. The other common use cases that we'll see with the cloud connections will be remote maintenance, where you have expensive equipment that's needs to be maintained by trained operators, and it becomes in the business interest of the factory operator to allow the seller of the equipment to access their equipment after it's been installed. And so we'll have a very simple or very restricted connection coming in to allow an authorized user to connect to that equipment and only access that equipment. All of the features that we're going to be talking about today in UA are set up to allow that kind of operation to happen and allow it to be done securely. So when I talk about security in UA, it's important to sort of go back and think about our overall vision for UA. And from the very beginning, we have been saying that security has to be a first-class concept. That every aspect of the specification, it's always, what are the security implications of this? What are the security, do we have to add in rules, or do we have to add in APIs that to address potential security risks? And we repeat that over and over again as we go through, and we've been expanding the specification and developing additional features. And so what we believe we have now is a very cohesive security solution that pulls in seamlessly different features that provide the complete security solution, and they all interoperate and they all interact with each other very, very cleanly. So I'll be talking a lot about each one of these topics today, starting with the communication security and how that works. I'll be going into application and end user authentication, and how that works, and the distinction between the two. I'll be talking about roles and role management and assigning permissions, which is necessary to control access to what any individual what can be done within a server. Auditing, how do we handle that problem? And lastly, and most importantly, management, centralized management of your security configuration. And I'll be talking about what we do to solve that problem. So the basic operation of UA is based on a client connecting to the server and exchanging a series of request-response messages. And to do this, they have to negotiate what is called a secure channel. And a secure channel is an abstraction representing a set of cryptography keys that can be used to secure the messages. In UA, the messages are secured, not sort of bytes. And this is important because what it does is it allows us to apply the security at a higher level and simply pass in the resulting envelope into whatever infrastructure you have to get bytes across the wire. So this creates a very powerful layered architecture that over time will be able to adapt as technology changes, and more importantly, allows you to send information across completely untrusted networks through multiple hops and multiple intermediaries, and be assured that by the time it gets to the destination, it's still secure. It hasn't been decrypted and analyzed by an invisible HTTPS proxy or similar entities which exist in the real world when you're dealing with simple web communication. Now with UA Pub Sub, it's designed for a much more loosely connected environment where you have publishers pushing data out to subscribers that may not even be online at the same time as the publishers, and this is all built around some sort of middleware such as an MQTT broker. It also works with UDP and UDP multicast, which is important when you're working on the control network. In these cases, because you don't have a channel or any sort of persistent connection between the publishers and the subscribers, the security has to be handled slightly differently. And the way we do that is we have this specialized UA server called the security key server that knows what access groups exist, who has access to the keys, and is able to provide the keys to anybody who can prove that they have a right to them. And so what happens is that the publisher starts up, it gets its keys and uses those keys to secure the envelope and sends it out to the middleware. The subscriber gets the message from the middleware, and then it can go and pick up the keys from the security key server, which will then allow it to read the message and do whatever else it needs to do with it. The security key server itself, in this diagram, we show it as a single box, but it's just an abstraction. The reality is you can have as many security key servers as you need, or they could be, depending on what your network, what your application architecture requirements are. So in the simplest case, the publisher would be the security key server. So the subscribers would just connect back to the publisher to get the keys. In other cases, you could have a publisher sitting behind a data diode pushing data out, and it would have access to its own security key server. Meanwhile, subscribers would be accessing a different security key server that's designed to be able to produce the exact same keys at the exact same time, but will be a physically separate process installed on a computer that's outside of the data diode. And thereby you've got a very powerful mechanism to securely send information across these very, very restricted network environments which are needed in some factory applications. Now with UA, everything is kind of centered on the application, or in the specification you hear the term application instance. And an application instance is a particular software application installed in a particular location. And I'm using relatively vague terms because in redundant scenarios, you can have multiple computers with a single application, or you can have an application that has multiple processes that are communicating with each other. It's intentionally vague, but conceptually there is this concept that if you have a software running on particular hardware, that is an instance of an application. So if you have 6 PLCs installed and they have the exact same software, they're all clones of each other, you've got 6 different application instances. So each one of these instances has a unique identifier that identifies this application to anybody else it's communicating with. This identifier, we call it the application URI. It shows up in multiple places, in multiple structures, and it's basically used to trigger logic that depends on the application you're communicating with. Independent of the application and then its identity, an application will have multiple ways to get to it. So each one of these ways to get to it is called an endpoint. And these endpoints could have different security protocols, whether you're coming in via TCP or you're coming in via HTTPS, or different security and have different security requirements, whether you're using signing or sign and encrypt. And also you could have different networks. So if you have an application that is sitting on a device that has multiple NICs because it's a bridge between 2 different physical networks, such as the control network and the operations network, then you'll have multiple endpoints for each one of those networks. You also have situations where you have redundant network technology. So then you would have to have multiple endpoints for each redundant network. However, the application developer decides it needs to organize its systems, you end up with a single application having multiple endpoints, and then the client, if it wants to communicate, it has to select the endpoints that it needs. So the endpoint are described in this structure called an endpoint description. It has a lot of the basic information that's there. One of the things we try to do in UA is to give people sensible things to do if they have no other information. And the security level is one examples of that. So it's basically a number that's stuck in it. So you go to the client, goes to the server, it says, give me all your endpoint descriptions. It gets back a list of 10 descriptions, and the client needs to pick one. Well, if it's got no other information, it picks the one with the highest security level, and then it's good to go. It doesn't need to do any more thought or have any more logic than that. The other thing, of course, is that if you don't have the structure and all you've got is a URL, or for that matter, if all you've got is a host name, UA has mechanisms so you can basically bootstrap information. You create a default endpoint description, you connect to the server, and then you can get the rest of them. And then from there, you can trigger whatever additional process logic you have to select a particular endpoint that is relevant for your application. Now, security policies are how we ensure interoperability securely. So we've defined as part of the specification a number of pre-canned suites of algorithms. We work very hard to keep the number of security policies as small as possible, because the more we have, the more your test matrix blows up. So we try to make sure that they stay few. But at the same time, we have to make sure that the policies that we have are secure. And that means over time, this list of policies is going to expand. But at any given time, we will always have 2 policies that are going to be recommended. So if you're doing any sort of greenfield development, then you will be able to go in and say, okay, what's policy A? Okay, that's my fastest recommended policy is going to be policy A, and policy B is going to be slower, but offers better security. So you don't need to think about the details of everything else. If you're an application developer, or if you're a system integrator, all the details of implementing these policies are taken care of by whatever commercial or open source software you're building on. But if it comes down to configuring your application, you're trying to make these choices, you can look at the security policies, and you should always try to focus on using either the A or the B option. Obviously, for backward compatibility, because this set changes over time, there will be times when you have to use something different, because that's the only way to communicate with some software that was released 5 years ago, and that would drive it. But that's a decision you make on a case-by-case basis. Now, I touched on it before about how you have this secure channel, and you've got this virtual sort of connection that is being set up when a client is communicating with the server, that allows you to create the context, which is used to ensure integrity of the messages that are exchanged. Now, this is sort of a more detailed view of that, but what I want to point out here is sort of the 3 tiers of interaction. So at the lowest level, you have your transport technology, your transport layer, and that is the physical bytes about the wire. And then you'll have to create this virtual secure connection called the secure channel that ensures the integrity of your communication. There's a handshake that goes on that takes advantage of PKI cryptography, and we support RSA and ECC cryptography depending on what the needs of your system are. And once you've got that secure channel in place, you then have to create what we call as a session. A session is where it stores the client, the server stores state on behalf of the client. The biggest part of this state will be the user credentials, which I'll be talking about in a minute, as well as what rights that those user credentials or this particular client has. And the rights and the authorization is all based on the session. So far I've talked about applications and sort of like how do they communicate? How do you connect? How do you get the data? How do you send the message across? How do you establish a connection? And how do you make sure those messages are secure and kept and unchanged? But that's not enough for a security solution. It's not enough to simply encrypt the bytes on the wire. You have to know who you're talking to. And that's what application authentication is. It's knowing who your peer is. And in UA, application authentication is done with a certificate. Every application is issued a certificate that has its identity. As I mentioned before, this identity is its application URI. Server applications will also be tied to particular DNS addresses, or IP addresses, depending on your network installation. So those are sort of supplemental information, but the primary identifier is the application URI. The certificate also has a human-readable subject name that is used to display in UIs if you have to do something, if you have to put some information up. But there's no requirements in terms of what goes into the subject name, but there's certain conventions that are generally adopted by different software in terms of automatically generating suitable subject names. So when a client connects to a server, basically when the client connects to the server, what it does is it looks at the certificate, verifies the certificate, and makes sure that the application URI matches what it expects. The server does the same with the client. And so you have the cryptographic operations that happen when you establish the secure channel are used to prove that the peer is who they are, who they claim to be. Now, the last thing that has to happen once you've authenticated the certificate or the application is you have to determine whether or not that particular application is authorized. And that's where trust lists come in. In UA, authorizing applications is called checking if an application is trusted. So if you're sitting debugging OPC applications, you will be caught. One thing you'll be seeing a lot in the documentation is does the server trust the client? Does the client trust the server? And what we're talking about is having some configuration in the client and some configuration in the server that says, in a server that says this particular server trusts this client and will allow a connection. Similarly, the client has to trust the server. And this level of authentication is sort of the need for mutual trust gives factory owners very tight control over who's allowed to talk to who. And this is a very important feature in any kind of factory environment when you want to make sure that you want to protect your system from either malicious or accidental exploits. Now, the way we handle this determine this trust is we leverage the PKI infrastructure. This is the public key infrastructure where you have certificate authorities who are trusted to do whatever, force applications to go through whatever administrative steps are required to verify that they are who they say they are, and then provide them with a certificate that's been signed by the authority. And everything hinges on the authority doing its job properly and only issuing certificates to people who are authorized to do it, which means that you have to have very tight control over which authorities that you choose to trust. When you are authenticating a certificate or validating a certificate, it's another term that we use, you have to get the chain, which is basically the link from the certificate, from the application certificate, through each of the certificate authorities back to a root. And that's called a chain. So the trust list that every application has is a physical store. It has to be stored physically on disk somewhere. It could be a database, it could be a registry. There's different options, but that the details are not important. It's left up to the individual application. But each trust list has two distinct stores or lists of certificates. One list is used for authentication. That's the issuer certificate store. It basically contains all of the certificates that are needed to verify the integrity of any certificate that's provided. So if an application presents an application certificate that's signed by a particular CA, then the issuer certificate store would have that CA in there, and the server would be able to verify that that the application certificate is indeed valid and was actually issued by that CA. The trusted certificate store is where you put certificates that are authorized. And the way authorization happens is there has to be one certificate in the chain has to be in the trusted certificate store. So it could be the top level one, the root, or an intermediate, or it could be the instance, depending on the level of control. If an application has the root certificate authority in the trusted certificate store, then every certificate that can be traced back to that root is, every application with a certificate that can be traced back to that root is allowed to communicate. And that may be a perfectly acceptable a level of security for many applications. For others, it's not. It's up to the administrator to decide the authorization rules and put the appropriate certificates into the trusted store, certificate store. Now, the process for authenticating a certificate is detailed in Part 4. There's a lot of different steps and a lot of different error codes. And if you're sitting there debugging your system, you probably will have to refer to this reference to sort of better understand what went wrong. One important concept to remember is there's two types of errors. There's suppressible and non-suppressible errors. Suppressible errors are things like expiry time, where yes, it's an error, but in some situations you can choose to ignore them. Errors are not suppressible, meaning that you simply cannot connect as long as those errors exist, and fixing those errors may require that you get new certificates issued to the applications. So the distinction between suppressible and non-suppressible errors is clearly laid out in the table in Part 4, but the important thing is all errors have to be logged, and there always has to be this log that servers and clients use to store the results of the validation exercises. And these logs are essential to helping people debug any sort of connectivity problem. And this is in part because security concerns have forced it to be deliberately cryptic. So clients, when they connect to the server, they're going to get back a generic error. Security checks failed. And the reason we have to do this is because any sort of error code allows malicious actors to learn about your server and potentially find ways to exploit it. So the only thing the clients get back is security check fails. But that's why there has to be a log. And that's why if any certified product, the first thing, one of the things that the test lab will look for is that the log is there and it's reasonably accessible to allow people to see the true reason for the failure and allow you to and make it easier for you to fix it. So here's a few common errors and common resolutions that people run into. The hope is that a lot of these kinds of issues and troubleshooting issues will be get baked into software as application developers learn about the challenges of debugging failing connections and provide proper guidance to user and sensible prompts. Sensible prompts to allow users to properly fix security problems. Simply saying, would you like to ignore this security issue and pretend it never happened, is not really an acceptable way to do it. But this is something we're going to be encouraging with our certification process, encouraging through education. But it seems complicated. It is complicated. But if you want to have a secure system, you can't avoid having these kinds of issues show up at the lowest level when you're setting up and configuring a system. But once you've done that, and once you've gone through that process, there's no reason why your system can't operate seamlessly without anybody really needing to know or understand these kinds of details. So you have the applications. We've gone through the process of authenticating and authorizing applications, but that's often not enough for real-world applications. It's not enough to know that you've got a application running on a local HMI panel that's connecting to my PLC. You want to know what human user is sitting in front of that panel. So in UA, we've introduced the concept of user authentication, where user credentials are passed as tokens when a session is created. And if you remember in the previous slide, I talked about the 3 levels. You've got the communication level, you've got the secure channel level, and you've got the session level, where you have state information stored on behalf of the client. And one of the things that's stored is this user token. And these user tokens, you have different options. Anonymous is just a placeholder. Username, password is a standard. It's simple, it's easy to understand, but it's also strongly discouraged, because having a bunch of passwords distributed among multiple devices on your factory floor gets very hard to manage very quickly, even though we have some APIs in place that allow you to manage some of this stuff. X509 certificates are for use with smart cards. So every employee has an ID card. They plug it into a slot on the computer, and then that has a certificate that's then passed onto the server. The most interesting, and basically the way that we want to see applications move in the future, leverages Java Web Tokens or JOTs. And these are based on the premise that you have a centralized authorization service, and this authorization service is capable of deciding who is authenticating a user or authenticating an application, and deciding what they have access to, and then providing a token that can be used to identify that user or device to server. So this is exactly what happens whenever you go to a website and you see a little button, log in with Microsoft, log in with Google. You click on that, you go to the Google authorization service, you type in your Google credentials, and then it will produce a token that is then returned to your original website. That token allows your website to then know that you are such and such a person with this particular Google credential, and will allow you to access resources based on that identity. Exact same process is happening, exact same standards that are being used here. The difference is that we've integrated it seamlessly in with the UA concept. So you go to a server, get your endpoints. You get back an endpoint description that has a user token policy. The user token policy says if you want to get a token, you have to go to this authorization service. You go to an authorization service. You ask for the token. You go back to the server, say here's the token. The server will then validate the token and then say, okay, great. I'll give you access to something in my server. Specific points about these access tokens, they are specific to a server, and this is by design, because one of the problems with username passwords, once you've got that password, you can use it anywhere and any way you want, and that's a huge security flaw. So when you're dealing with access tokens, if you want to connect to one PLC, you need an access token for that one. You want to connect to a different PLC, you need a different access token. And of course, access tokens expire, which means you have to be constantly renewing them, which again is it's a necessary security feature. However, and it requires a little bit extra logic. But the benefits, once you have all of this stuff in place, in terms of centrally managing your user identities and your access control, is going to be simply too large to ignore for most installations. Once you've authenticated a user, you need to decide what that user is allowed to do. So that's where the role and permission model comes in. In UA, we have a standard way of assigning permissions to every node in the address space, and these permissions are assigned based on roles. These are abstract concepts that are used to represent different permission sets that are different either actors or use cases. Depends on what your system design is, how you want to structure your roles. And this allows the permissions to be set in a way that's completely independent of the mechanisms for actually providing user identity. So it can be configured, and more importantly is the roles and the permissions can be set centrally or it can be set for a device without, and then simply reused as it's installed in different locations, because the only thing is that each installation you've got different users, and you'll have to have a different way to map the users onto the roles. But the roles themselves and the configuration doesn't change. And mapping rules are how you do the translation from the user onto the role. Now, with mapping rules in UA, it's not limited to a simple, okay, if user X, then you're in role Y. It is a combination of multiple criteria. So you have the actual username, but you also have the application. So you can have a role that's only accessible if user Joe is logging in from the HMI panel at station 1. And you can add another criteria. You say, well, okay, for this particular role, you can only get access to it if you're also using an encrypted channel, because this role grants access to sensitive information. Other roles may not require that encryption because the information is not as sensitive. So these mapping rules themselves, there's APIs in place to allow them to be remotely managed and remotely configured. It would be integrated in with whatever authorization service you have. So over time, you would expect to have an authorization service that's able to push out the mapping rules to the different devices as the requirements change over time. But of course, that's just one way to do it. You can have the server itself allows you to modify them. You can have a specialized engineering tool for the server that modifies it. The options, there's a large number of options, but the important thing is UA provides standard APIs that allow you to build applications that can remotely manage these mappings. Auditing. Very, very important part of a complete solution. In UA, we define standard structures for different types of events. We basically define the number of fields, some of which are mandatory, some of which are optional, that have to be filled in whenever a particular event occurs. So a session is created, a certificate is validated, a variable is written to. All of these different activities which are potentially security sensitive would produce an event. And these events can then be reported using any number of mechanisms that depend on the server. And the obvious one is that it could be reported as a simple UA event. And you could have a UA client, let's say an audit logging client that subscribes to all the servers and gets these audit events and stores this in some sort of historical database. But it's not limited to that. Servers can certainly write the audit events locally to a log, or it can report them via some non-UA mechanism such as syslog, which is popular in a lot of situations because there's off-the-shelf tools that can receive these events. But no matter what you're doing, the structure, all the structure and semantics, in particular, when these events are produced and what information goes into these events is the same. And this is all standardized by the specification to allow multiple different applications, to make sure that different applications and different vendors work the same way. If you know that if a certificate was validated, they're both going to produce a validation event and it's going to have this information. The last and the most important topic has to do with centrally managing all of the authentication and authorization configuration of servers. Now, this is built, the concept that we've introduced in UA is the idea of a certificate manager. Now, if you've been watching any other presentations on UA, you'll see some discussion of a GDS or Global Discovery Server. This is the certificate manager. It's basically a feature inside the GDS is certificate management. It provides an API to a certificate authority that allows applications to request certificates and, most importantly, request the trust lists that basically tell them who they're allowed to communicate with and which can vary from application to application. So in UA, we define these standard APIs so we can encourage third-party vendors to put together solutions. There's at least one solution on the market today, and there's another one that will be coming out in the next couple of months, and we hope there'll be many more, because we know that if you're going to be deploying large numbers of UA devices, you need to be able to manage these certificates. And in parallel to this, effort in terms of encouraging third-party vendors to provide these products, we also, through our certification program, are making sure that anybody who develops UA applications interfaces with a certificate manager. So you can be assured that if you buy a third-party product and a certified UA application, that they're going to interoperate with each other. Now, with managing certificates, there's two different ways that it could work depending on the type of application you have. In the pull mode, the application is a client of the certificate manager, and it connects to the certificate manager, and it can request new certificates, and it can update the trust list. This is a process that will be done once initially, but then repeated over and over again, because certificates expire and trust lists have to be updated. In particular, certificate revocation lists have to be updated. And so you would either have some sort of background task on all of your client applications, or more sophisticated servers that are going to be doing this. The certificate manager also operates in pull mode or push mode, where and this is primarily for lower end devices which only have server capabilities, where the certificate manager or software agent acting on behalf of the certificate manager will push the certificate up to the device, as well as provide the trust list and other configurations, and a trust list, and it will do that periodically as required, whether to renew the certificate or to update the trust list and CRLs. So there's probably a lot of questions that have come up because I've touched on a lot of very complicated topics, and I've had to leave a lot of material out in order to make sure that this presentation was kept to a reasonable length. But I hope it's given you a suitable introduction that will give you a better idea about how to develop and deploy UA systems, secure UA systems.